Hi guys, this is Dr. Anna, and we are in the third segment of the first module in the historical geology sequence, the geologic time. In this segment, we're going to talk about the geologic principles. These are very important for all of us because you are learning about historical geology. I'm a geologist, so we all need this. I will ask these on the test, so they are very important to know them. And in the labs, you're going to use it so you understand better how the geologists work with these principles. So we got to learn the principle of superposition, original horizontality, lateral continuity, the cross-cutting relationships, principle of inclusions, the famous uniformitarianism, the one you have to kind of practice how to pronounce it. We have to talk about the principle of unconformities and the faunal succession. We're starting with the first one, which is the superposition. When you have an undisturbed sequence of sedimentary layers, logical that the oldest layer is always going to be on the bottom because that's the first one which went down. If you look at this little example, when we pour sand into a glass tube, the first sand is the oldest, and whatever you put on top of it are always going to be younger. So here is the oldest, and that's the youngest. So the principle of superposition is extremely simple and it's very easy to remember. The next one is the original horizontality. Sediments settle out from water under the influence of gravity and are deposited in approximately horizontal layers. So as you can see here, this is the basin, let's say a lake, and the sediment which settles down will most likely be horizontal because of the gravity pulls the grains down. So that's very simple as well. The second one is the principle of lateral continuity. When you have a lateral continuity, that just means that in the sedimentary basin, typically deposited over vast areas, like if you have a little bucket and you were playing on the beach and you put sand in the sand went all the way in the passable area. See? And if you change the color, your next layer of sand will go in the whole, we could call it sedimentary basin. So it fills up the whole available area. And it's the same in real life. Like you have a lake or an ocean, the sediment just fills up the whole area possible. And if later anything happens, like a river cuts into that sediment, it just cuts it out. There's another channel. See? But we know that originally these guys were all going all the way through. So it was like a horizontal layer all the way through because it continued laterally. And then later something happened. The next one is the principle of cross-cutting relationship. This is really cool. And it's really important that you will understand that when you have sediments and they deposited horizontally because of the gravity, as I just told you, and then there was a volcanic activity in the surrounding area, and the dike went through here. See, it went through all these layers. Therefore, it has to be younger than the layers it went through. See, so this dike, when it came through, all these layers, oldest to youngest, were already there because it went through them. So if something goes through those layers, then the something which goes through has to be younger than the layer it crossed. So this is the principle of cross-cutting relationship. So when you go through something, it had to be, whoever you went through had to be there so you could go through. So an igneous intrusion or fall that cuts across a rock unit must be younger than the rocks being intruded or displaced because if they were not there, it wouldn't have gone through them. So you understand, I hope. The next principle is the principle of inclusion. And when you have principle of inclusion, that just means that you go to the beach, you see a rock, and in the rock you see pebbles. Those pebbles came from another rock, which eroded away and become pebble. That means that the rock, which includes the the pebble got to be younger than the pebble because the pebble wasn't a rock before. So here, components of sedimentary rock must be older than the time when the rock was deposited. So if you have pebbles, the pebbles are always older because it's coming by erosion from a different rock. So it's kind of interesting and easy to understand. So inclusions in igneous rocks are older than the rocks containing them. So if you had a metamorphic rock, it eroded away, made pebbles, or another magma came through and broke it up and took it with it, and now it's in the igneous rock. That means that that rock which the igneous rock includes is older because it came from another rock. So I hope you understand that too. And the principle of uniformitarianism is really amazing because this is the one by which we know that all we have to do is to find a sedimentary environment now which produces something which what you're trying to figure out what it is. Like right here, this is the beach. And you do know because you've been on the beach that the ripple marks are forming by the currents of the ocean. Or if you are in a river valley and you see ripple marks, you know that the ripple marks formed by the current of the river. So if you go back in time and you walk on a rock surface and you see ripple marks, which look just like the one on the beach, that you know that these ripple marks formed the same way as these ones today. So this is the amazing thing about the uniformitarianism that it opens your mind up and you can explain everything because all you have to know is how does it happen today, and then you know that it would have happened long time in the past in the exact same way in the exact same kind of environment. So it's really a beautiful principle of uniformitarianism. Now these are the principle of unconformities. When we're talking about unconformities, we're talking about missing time in the rock sequence. We can also call it hiatus, meaning during that time there was no deposition and no rock layer preserved. So that always means some time is missing from the rock layers. How much time is missing? It's really hard to figure out, but we have some kind of evidence, just somewhat about the missing time. So we have four kinds you will have to know: the non-conformity, angular unconformity, disconformity, and that is the paraconformity, but it's really hard to recognize. So I won't really know the non-conformity, angular unconformity, and the disconformity. You're good to go.
This boundary is an erosional surface, and it is a spectacular example of an unconformity. An unconformity is a buried erosional or non-depositional surface between strata of different ages. But what does this mean? How do unconformities form? And are there different types? To begin to answer these questions, let's review erosional surfaces. Erosional surfaces are surfaces produced by the removal of rock or sediment. They were produced in the past by weathering and erosion. Rocks exposed on the surface of our planet are constantly being broken down into smaller pieces through the process of weathering and transported from their place of origin by the process of erosion. The agents of erosion are gravity, wind, running water, and ice. This image shows you the sequence of events leading to the formation of an erosional surface. Let's walk through it together. At time 1, there is deposition of strata, layers A, B, and C. These layers are deposited underwater through sedimentation in the ocean. During time 2, these layers are uplifted. The strata rise above sea level, so they are no longer located underwater. Because they are above sea level now, there is no more deposition or sedimentation. They are exposed to the elements, gravity, wind, running water, and ice. During time 3, these agents cause weathering and erosion of rock. Stratum C is completely destroyed, and so is part of stratum B. Stratum B becomes truncated. Finally, during time 4, the strata are subsided. The layers sink back beneath the ocean, and there is new deposition and sedimentation. Because stratum C was completely destroyed, the new sediment, stratum D, is deposited directly on top of what's left of layer B. We call the contact boundary between stratum B and stratum D an erosional surface, as it records when and where the layers were exposed above water and rock layers, stratum C, were destroyed. Another way of thinking about the erosional surface is that it represents missing rock corresponding to time that we can't study. Erosional surfaces form during periods of time when there is no deposition of sediment. Not to mention, the strata beneath them tend to be missing and truncated. Rock layers are missing. You aren't seeing the entire history of deposition and sedimentation. Erosional surfaces are generally illustrated in geologic sections as wavy, irregular, undulating lines. Often enough, you will see abrupt changes in lithology across lines of erosion, as well as the termination of fault lines and intrusive rock. In this example, notice how the intrusive rock R was eroded away along with the sedimentary rock layer X. Once sedimentation resumed, the new rock B formed on top of both R and X. We call this a cross-cutting relationship. Of course, unconformities can also help you to identify erosional surfaces. At unconformities, rocks do not conform with each other across the line of erosion. The line may mark a significant change in the lithology of rock. For example, there may be igneous rock below the erosional surface and sedimentary rock above it. Alternatively, the erosional surface may mark a big change in the orientations of the strata, like the erosional surface at Telheiro Beach in Portugal. There are actually 4 types of unconformities. I find that the best way to learn about unconformities is to learn how to distinguish these 4 types. The erosional surface at Telheiro Beach marks an angular unconformity. Angular unconformities are easy to recognize. At angular unconformities, horizontal strata lie on top of tilted and eroded beds. In these cases, the lower strata were first tilted as a result of plate tectonics and then truncated by erosion before the upper strata were laid down above and parallel to the erosional surface. Let's take a moment and walk through this process step by step. The principle of original horizontality tells us that all strata are laid down in horizontal layers. And the principle of superposition tells us that the oldest layers occur near the bottom. So strata are laid down in order, one after another, and so on and so on. Sooner or later, however, sedimentation may stop. No more layers may be deposited for quite some time. During this hiatus in sedimentation, tectonic forces on our planet may fold, distort, or simply tilt the layers. Like all other rocks on the surface of our planet, these tilted strata are subject to weathering and erosion. The processes would destroy and truncate the rocks, producing an erosional surface. Eventually, sedimentation would resume at this location, and sediment would be deposited on top of the erosional surface above the truncated layers. Again, the layers are laid down, one after another, and so forth. Overall, this is the natural process that produces an angular unconformity. It's a long process. It can take tens or hundreds of millions of years or longer. Another type of unconformity is called a nonconformity. Nonconformities are generally easy to identify if you can recognize the differences between igneous, metamorphic, and sedimentary rocks. At nonconformities, sedimentary rock layers occur on an erosional surface located at the top of much older igneous or metamorphic rock. How do you know that there is an erosional surface here? Igneous, metamorphic, and sedimentary rocks form through very different processes and under very different circumstances. There must have been enough time for erosion as well as a change in conditions between these rocks being formed. Disconformities are harder to identify. In these cases, sedimentary rocks occur on both sides of the erosional surfaces. The best way to recognize a disconformity is to attempt to identify the erosional surface. This erosional surface truncates the lower sedimentary strata, and it is usually quite irregular. It may contain cave or karst-like structures, root traces, and other signs of weathering and erosion. Of all the types of unconformities, however, paraconformities are the hardest to see and recognize. Like disconformities, paraconformities consist entirely of sedimentary rock. However, instead of an erosional surface, there is only a surface of non-deposition. There is no evidence of weathering or erosion. The sedimentary strata on opposite sides of the surface seem to be conformable. There is no obvious evidence of missing rock. The boundary is regular. You usually need the absolute ages of the strata or fossil evidence to show that there is missing time or missing rock in your sequence. Learning to recognize and distinguish unconformities are important steps in becoming a historical geologist. With this knowledge, you can begin to look at geologic cross-sections and determine the sequence of events that led to the structures you find. We call this process relative dating. It is the science of determining the relative order of past events, such as deposition, erosion, intrusion, and faulting. It is the key to traveling backward through time, through Earth history.
Next, I'm going to show you all these things put together, what we just learned about the principles and the unconformities, and we're going to use the Grand Canyon as an example. So this here is the cross section of the Grand Canyon. You see all the layers which is exposed in the Grand Canyon as you go down to the river. Here is the river, and that's the surface right here. So we can see a couple of unconformities. They're all a red line. They also say that it's non-conformity. So we have between igneous and metamorphic rocks non-conformity as an unconformity. Along this non-conformity, the metamorphic and igneous rocks meet with sedimentary rocks. Okay, the next unconformity is right here. And because I'm going to draw it like right here, that's an unconformity, see? And look what happens. These layers coming up with an angle. So therefore, it's an angular unconformity. And then you can see this unconformity. And because the layers parallel below and above, this is what we call disconformity. And you can see there is another one of those. So the layers below and above are parallel, so it's also a disconformity. So on this slide, we have non-conformity between these really old rocks and the sedimentary rocks. We have the angular unconformity right here and two disconformities. I also have this arrows coming in. So you see they show, this one shows the angular unconformity and that one shows the disconformity. And that's like really point to the nonconformity. Okay, so now I have a cross section here, which is very complicated, so don't feel too bad if you don't understand. I'm going to try to explain. So in this figure, the first thing which happens is this B, which actually shows all these sedimentary layers. So this is a conglomerate, let's say a shale, a limestone, and another shale layer. And as you can see, these sedimentary layers are messed up by a couple of faults and a couple of intrusions. This fault is the E fault, and you can see that that fault didn't displace the D, the black igneous dike, so it's an igneous intrusion. But at the same time, the C is being crossed by this D dike. And then the A fault faulted the dike, the D dike. So with that, using those, we can actually put together which one is oldest and which one is youngest. So we can do the relative age dating. And then you can measure absolute age data on the igneous rocks so you can figure out how old is what. So obviously the B is the oldest because all these layers had to be there to be cross-carried and faulted. So after the B, we have this E fault because the fault didn't faulted the dike, so therefore the E fault had to be here after the B. Because the E fault faulted all the layers, all of them, as you can see. But after that, look at the A fault. The A fault faulted the dike. So the dike was there before, and this dike crossed the C, which means C had to be there before the dike. So after E comes the C, and after the C comes the D, the dike. And after the dike comes the fault, the A fault. Okay, so as you can see, it's like that. So you really carefully have to see what is crossed by what, and then you can figure out which one is the oldest and which layer is the youngest. I just said old and young. So I hope you understand. It's not very simple. This one is a pretty complicated example, but we have in the lab, you will see I have really simple ones and then gets more and more complicated. So you will be able to work it through. Oh, and it actually shows you. So the B is example of superposition because this is the oldest and this is the youngest here. And then cross-cutting relationship, of course, I already kind of mentioned that to you. And then original horizontality, of course. So basically that figure showed everything. Okay, the last principle is the principle of the faunal succession. And as you know, evolution is one-way street. So therefore, if you had a fossil, then it will never come back. So therefore, we can use those fossils to do relative timing because they only occur at one time. So if you see that fossil, you can even correlate with them, which is really good because you can tell that this is the same time, like wherever it is on the world, like it's in the United States or in Europe, you know that the layers which have the same kind of fossils have formed at the exact same time. So that's how the whole time scale can kind of get together using the principle of faunal succession. So that's just the most important thing that every fossil only occurs one time in the geologic history, just that one time, and then it evolves into something else. I'm going to finish this segment right here, and we're going to continue with the absolute age dating in the next segment. I'll see you there.